Hello everyone, my name is Sangwon from KAIST. I would like to present our work, the TensorPRAM. Nowadays, the deep neural network have gained huge attention for a wide spectrum of applications, including visual understanding, speech perception, automated reasoning, and so on. To accelerate the deep learning process, various kinds of approaches have been suggested. Among them, FPGA-based hardware accelerations are known as one of a promising solution. However, for the data processing with a conventional FPGA-based accelerator, there is data movement overhead between a host and an accelerator. This figure shows a typical computer system with an accelerator. If the accelerator needs to access the data from the host side storage media, data needs to be copied from SSD to device memory and travel through I/O controller, node bridge, and arrive host side memory. Then CPU access the data from host side memory and copy the data to user process, which runs DNN computation. Finally, the data in the user process is again copied to accelerator size DRAM. To reduce the time for data movement overhead, we suggest TensorPRAM. The TensorPRAM replaces the conventional DRAMs with the non-volatile PRAMs in an accelerator. With non-volatility of the PRAM, we can store the DNN data in the PRAMs. Therefore, the accelerator can access the data directly from the PRAM. For evaluation of the TensorPRAM, we compare the TensorPRAM with the other two types of accelerators, CPU-X and DNN-X. CPU-X uses a single-core general-purpose processor with DRAMs, and DNN-X uses DNN acceleration logic with DRAMs, and the TensorPRAM uses DNN acceleration logics with PRAMs. We use MLP multi-layer perceptrons as evaluation workload. Firstly, we compare the execution cycles. All the results are normalized to the execution cycles of CPU-X. DNN-X reduced the execution cycles compared to the CPU-X by 580 times on average. And the TensorPRAM improved the performance compared to the CPU-X by 1,350 times on average. Next, we also broke down the execution cycles of each type of accelerator. In the CPU-X case, the host data movement overhead looks relatively small because the CPU-X spends most of the cycle to perform the matrix multiplication. But the overall execution cycles are very long. However, the data movement overhead of DNN-X accounts for 60% of total execution cycles, which is fairly large. In contrast, the TensorPRAM reduced the data movement overheads considerably. Lastly, we compare the consumed energy for each accelerator. As you can see in this figure, the DNN-X consumes less energy compared to the CPU-X by 99%. And the TensorPRAM further reduced the energy consumption compared to the DNN-X by 61% because the TensorPRAM reduced the energy consumed for data movement. In conclusion, we propose TensorPRAM, which is a deep learning accelerator implemented on FPGA with an integration of PRAMs. And our TensorPRAM outperform the conventional DRAM-based accelerators in the execution cycles and energy efficiency. And these performance gain and lower energy consumption in TensorPRAMs are contributed from the reduction of the data movement overhead. This is the end of my presentation. Thank you for listening.